A-level physics lesson 59, all about energy and efficiency. And this is the last lesson of the work, energy and power topic. It's a small topic and I don't tend to bother teaching it for very long when I'm in school because most of it's just GCSE level with a little bit extra. But here we go. A reminder about efficiency at GCSE level. At GCSE level, you learned that efficiency, and I'll use the symbol epsilon for this, is defined as the energy that's been transferred usefully, is a lowercase e, energy that's usefully transferred, don't know how many R's in the word transferred. If it's wrong, go in the comments and complain. Divided by the total energy that is transferred. Usually this is written as the total energy that's put into the machine or the system. But yeah, there's still the total energy transferred. So we could write that as E out, and that's an E that's usefully transferred out, divided by the total energy that's transferred, which is the E in. As long as we remember that this is useful energy that's transferred. The energy that's transferred that's useful will be equal to the total energy that's transferred subtract the wasted energy. And wasted energy usually, especially in mechanical systems, waste energy, usually that is going into the thermal energy store of some sort of system, some machine. Yes, the energy that's transferred usefully is energy that's doing what you wanted the machine to do. So if we take, for example, a light bulb, the purpose of the light bulb is usually to illuminate the room. Call them lamps usually. We want to illuminate the room. The fact that the light bulb will also increase the temperature of the room is an irritating byproduct. So energy that's transferred by heating, by infrared radiation out of the bulb, or by conductive heating even out of the bulb, all of that is transferred in a wasteful way. The useful energy transfer is the energy that's transferred out of the light bulb by visible light radiation. Now remember that the radiation, the waves, they are not a store of energy. So where are those waves going is ultimately to the thermal energy store of the surroundings anyway. But some of it's transferred usefully because our eyes can make use of it, and some of it is not. And there are mechanical machines, simple machines like the what do you call it? The lift at a garage that lifts a car up so you can get underneath it. The purpose of that machine is to increase the gravitational potential energy store of the car, i.e. lift it up. But in doing that, there are going to be moving parts, and that's going to increase the thermal energy store. So energy is going to be delivered into our machine by a current, and we'll calculate the power for that, which we talked about last lesson. But then there's going to be a rate that energy is being transferred in a wasteful way because of the motor turning and the heating of the various parts and so on. So it's all very well to talk about efficiency in terms of energy, but it could actually be more useful sometimes to talk about energy efficiency, to talk about power efficiency, sorry, not energy efficiency, but power efficiency. So the power that is out, actually, let's do it the other way around. Let's say that the energy which is transferred usefully is equal to the useful power multiplied by the time that the appliance is running for. And it's the same for energy. So the total energy that's transferred into our appliance is equal to the rate of transfer of energy into our appliance multiplied by the time that our appliance is on for. Just like that. And so we could take each of these and plug it into that equation for efficiency, and we get power out multiplied by time divided by power in multiplied by time. And obviously the times will cancel there, so we don't bother writing them. We just write power out divided by power in. And again, I've used the notation power out, but this is useful transfer. And in the same way as we had before, this is total transfer. Let's put that like that, total. And the same way as we had before, we could say that the the useful power out is equal to the total power out, subtract whatever was wasted. The same idea. So we can have our energy efficiency equation in terms of power. Now, efficiencies are usually given as percentages rather than as fractions or as decimals. So this, and I'm going to put P out divided by P in, is actually exactly the same as this multiplied by 100%, because the percent means divided by 100. So all we're doing is times it by 100 and then dividing it by 100 again. But rather than writing that, we write the percentage symbol. So they are actually completely the same, except with one of them, you'll write it with a percentage symbol. So obviously 0.50 is the same as 50%. I don't think anyone's going to be too shocked with being able to convert between percentages and fractions and decimals and all this sort of thing. It's just a skill you need to have for A-level physics, GCSE physics, life in general. And usually the energy that's transferred wastefully, especially by mechanical systems, moving things around, is transferred into a thermal energy store. Now, the efficiency can never be 100%. It can get close to 100%, and we can make systems more and more efficient, but we can never be 100%. It can never be more than 100%, definitely not. There's no such thing as a perfectly efficient system, although, ask me about the brakes on a car, and I'm going to be finding it difficult to explain why that's not 100%. The purpose of the brakes of the car are to transfer energy out of the kinetic energy store of the car, and that's what they do. So I don't know, but no, I would say that there's no such thing as a 100% efficient system. Just be aware of that. Right, now there is one last little thing that seems to be just slipped on the end of this topic for no real reason, which is about energy resources. And we do have to be careful with this because energy resources are entirely different. Now, I'm guessing that when they designed this particular curriculum, they just didn't know where to stick this particular topic. So I'm actually going to give it a new title, Energy Resources, because it is not to be confused with energy stores at all. It is a different topic. I'm guessing that they just didn't have enough with the energy efficiency to call it the end of the topic. So energy resources, we don't need to know much more than GCSE. We've got our renewables, such as photovoltaics, photovoltaic cells, such as thermal solar panels, so solar heating panels, I guess I'll call them. Both of these could be rather clumsily called solar power. But we do have to be careful with that because they are very, very different. Photovoltaic cells directly generate a current, whereas solar heating panels, we can use that to generate a current if we use the water that's been heated up in those panels to make steam to drive a turbine. That turbine drives a generator around and generates an electric current. So we can generate a current with solar heating, but very often we just use the hot water for other things. What else do we have? We've got our friendly wind. We've got, I suppose, waves are experimental at this stage. Geothermal, which is very limited geographically where you can put it. Hydroelectric power, tidal power, yeah, biomass. You can burn biomass, biofuels, biogas, all that sort of thing. That's renewable as well. So there's a whole bunch of renewables here, and they the idea is that they don't run out during the duration of human civilization. That's not the official definition. The official definition is something like they get replenished faster than they're used, which I don't like as a definition. I prefer the idea that they won't run out during human civilization. But there we go. If I've forgotten any, do let me know. Now, why am I talking about this? Because one of the things that might be interesting is looking at the maximum possible power that you can generate with these sources. So we could look at hydroelectric, for example, and look at the rate that water can flow through our pipes. And the limit to the rate that water can flow through the pipes determines the limit to the rate that we can transfer energy by that water. But let's take an easier example. Let's take the example of wind. So, example of wind. And now in wind power, we will have our turbines that look a bit like this. Okay, and they can spin around in a circle. So they can spin around in a circle just like this as wind pushes them around. And maybe we're interested in the maximum power that can be generated by these wind turbines. So let's add some measurements to this. Let's say that the radius of the wind turbines, let's call that R, just like that. And that's going to have an impact. We also have the air moving through these wind turbines. And the air that's moving through these wind turbines, we can think of that as like a cylinder of air. So imagine the wind is blowing from left to right. From right to left. So let's take this, let's duplicate it. Come on. Let's pop it over here. Oh, battery on my stylus is running low. It should be fine. If it runs out, I'll quickly switch to the other one. This is the one that I was waiting for it to be repaired for ages, and I finally got the part and repaired it. So that's why I'm not having issues with the pen not working. But the batteries aren't very good on it, so I need to nudge that up. There we go. Anyway, that's me muttering away while I'm busy colouring in and deleting stuff that I don't want. So imagine a column of air. And we have some information about this column of air. We know the air's density, and we'll be talking about density in the next topic about materials, but you should have done density at GCSE. And perhaps the air is moving at a certain speed, v, and it's moving in this direction. So it's going to move through. So we could work out the maximum power that we get, or we can possibly get, from this wind turbine. Remember that kinetic energy of the wind is what we are transferring. That's equal to half times mass times velocity squared, and we know the speed. What we don't know is the mass. We do know that the mass of air is equal to the density of the air multiplied by the volume of the air. And of course, we don't know the volume of the air. What we do know is that the cross-sectional area of this cylinder of air that passes through the turbine blades is going to be equal to pi r squared. So the only difficult thing is knowing that the volume of the air is equal to the area multiplied by the length of that column. And we don't know what the length of this column of air is. But what we do know is that it's travelling at a certain speed, which means it travels a certain distance in a certain amount of time. So let's go back to my black pen. We can say that it travels, let's say v is that length divided by the amount of time it takes for that column of air to travel that length. So we've chosen that length so that that is the amount of time it takes for that column of air to travel it. Now, if we do that, that means that L is equal to V multiplied by T, which means that the volume is equal to A multiplied by the speed multiplied by the time. Okay, that means that the mass of air is equal to the density multiplied by the cross-sectional area multiplied by the speed multiplied by the time. But the cross-sectional area is pi times r squared. So it's pi rho v t r squared. I'm just taking these equations and putting them together. And then finally, that means that the kinetic energy that this air carries is going to be equal to, and then we can plug all this in. In fact, let's do this a little bit, bunch it up a little bit, because I'm going to need a little bit more room. So bunch it up just a little bit. Let's pop it up there. And then bunch that up just a little bit. Right, so we can say that the total energy is equal to 1/2 times by pi rho v t r squared v squared. Well, the v is appearing twice there, isn't it? We've got a v squared and then we've got another v. And if we divide through by t, so we end up with energy divided by time, that is the maximum power, would be equal to 1/2 times pi times rho times r squared times v cubed. There we go. So for this wind turbine, if we know the wind speed and we know the size of the turbine, the density of the air, we can calculate the maximum amount of energy that the air carries. We know the wind speed, we know the size of the turbine blade, and we know that the air density of air is about 1.2, 1.3 kilograms per cubic meter. And so we can use that to calculate the P, the power that is delivered. Now, not all of that will be delivered, because if it did, the air would just stop, and then we'd end up with infinite density air here as more and more and more air piled in and stopped moving. So we know that the air does have to have kinetic energy afterwards, and that the air will be more dense afterwards because it will be slowed down and bunched up. And so all we're calculating here is the absolute maximum kinetic energy that the air could possibly have. That is not equal to the energy that is transferred per second to the national grid. So we could then use that to calculate the efficiency of the turbines in terms of power and things like that. So that's the classic example. We could also look at solar heating and bring in the idea of thermal heat capacity, which you do in GCSE as well, but I don't want to go into detail about thermal heat capacity and all that sort of thing now. So I'm going to stop there and say that is the end of this section, all about efficiency and a little bit on energy resources and flow rates chucked in the bottom. I know I did this bit down here quite quickly. Oops, I deleted it. I know I did this bit down at the bottom quite quickly, but I don't think it's too bad. It's as long as you're comfortable with the algebra and you know what you're trying to calculate, just chugging through the numbers is something that an A-level student should be capable of doing. And if you're not, then practice. That's how you get better at doing it. Right. That's the end of this lesson and the end of this topic on work, energy and power. Next lesson, we start a new topic all about materials and we start with density. So I hope you'll join me then. Bye-bye.